Hello, it's Keith here, and this is the conclusion episode to the Grime Z80 project. Now, this is a few days after the finishing of the project. The project lasted 7 days, and if you've seen that series, then you'll know we got to the point where the game was basically finished and playable on all the systems. Now, over the last couple of days, I have made a few slight tweaks to the MSX2 version. If you remember in that video, I said that if I had more time, I would like to make the MSX2 version use the VDP better to emulate the tile map. I have now done that, and the results of that will be being discussed in my regular tutorial series when I cover the other VDP systems. But the result of this is, if you see what I've got here, this is now Grime Z80 on the MSX2. And if we just start the game, you'll see the game is now a lot faster, and we now have the proper tile animation like the other systems, and the speed is much more acceptable. I'm not sure if it's actually the same speed as the other systems, and to be honest, the MSX2 graphics system tends to work better with large sprites rather than small ones, so again, it's probably still not really showing off the MSX2's graphics chip with really any great finesse, but it certainly is now much more playable and reasonably matches the performance of the other systems. There is another benefit to this. The MSX2's internal graphics chip is very similar to the V9990, the V9K as it's sometimes called. Now, this is an external graphics processor that is much more powerful. Now, to be honest, I can just turn it on. If I just enable this option here and compile. Now, to be honest, there probably isn't much performance difference in game, because again, this is a graphics chip that works best with very big sprite. Oh, it is very fast. It works better with very big sprites, and this is a lot of very small sprites, so it will be much more delayed by the processor rather than being delayed by the graphics system. So as I say, it's probably not benefiting much, but there is one important reason that I've done this. Firstly, I'm planning on doing tutorials on how to use the V9K. So that's a benefit, but there is another benefit, and unfortunately it's a benefit I can't show you today, but this should now work on the Amstrad CPC with a V9K. I've rewritten my V9K driver for the MSX to use the new Amstrad converter, so that this game should in theory now work on an Amstrad CPC with that external graphics card connected to it. Now, as soon as I get that graphics card, I will do some testing, but at this stage all I can do is say it should work in theory. I can't test it. But anyway, that was just a little refresh on what's the sort of end work that I've done on this, because it was more because I wanted to cover that content in the tutorials, and as I've said before, Grime Z80 and the tutorials are sharing much of the same code base, so making it for one and making it for both was the same amount of work. I don't plan on adding any genuine features to Grime Z80 from now on. It was a test game, and that test game is finished. But anyway, today we're going to go over the entire source code of the main module and also the simple tile module. The rest of the code, as I've said already, is basically in the tutorials, and it will be covered in those tutorials. So if you're interested in knowing how Grime Z80 does its key input, for example, please look at the tutorials that I've already made covering that, or in the case of the Game Boy and the Game Gear and those kind of systems, those tutorials are coming very soon. So as I say, today we're just going to focus on the Grime Z80 specific stuff, and also the simple tile function, which was written solely for Grime Z80, and maybe I'll use it again, maybe I won't. So let's start then and have a look. So we've got these definitions, which are really for the Amstrad CPC. This is to define what system you're compiling for, but these scripts I've got here actually define these automatically. Screen width 256, that's always set, because that's just telling my generic tutorials driver that we're using a 256 pixel wide screen, even on the Amstrad CPC and the MSX, which have a wider screen. So then we have some definitions for each machine. The reason for this is we need to switch some modules off. Now the consoles don't have keyboards, so we don't read the keys in the same way. So that's what this function's for, to disable the keyboard passing function and just use a direct hardware joystick reading function. SXX is any Sega system. Sega Game Gear and Sega Master System are virtually the same. GBX is any Game Boy system. Game Boy Color and Game Boy virtually the same. And we've got the palette GB is for the special Game Boy palette. We also have a 4-color palette for the Enterprise and the Amstrad CPC. And generally for all the other systems, we have a 16-color palette. But the MSX one has a special palette as well. So that's what these definitions are. Now, build console is another function that disables certain functionality. Now, actually, the MSX, when the VDP is being used rather than the bitmap display, which is the faster option, that is also defined as being a console system according to this. Basically, that build console option means this system has a hardware display that cannot be treated as a bitmap. It has to be treated as a tile map. The difference between a bitmap and a tile map is a bitmap, you can go to any position on the screen, write a single byte, and it will appear as byte data. What it will look like will vary, but it will appear as byte data. Whereas a tile map display, you can't do that. You have to define a tile, which is 8 by 8 pixels on all of these systems, and then tell a certain location on that screen that location is going to show that tile. So the functionality is very different, and that's why this game works in 8 by 8 squares. It's intentional because that is the commonality between all the systems. The Amstrad CPC is 4 pixels wide, the Samco is 2 pixels wide, the Spectrum's 8 pixels wide, the Game Gear's 8 pixels wide, and the Game Boy's 8 pixels wide. The common thing, 8 by 8. So that was why this game was chosen, because it's a very simple graphical game, works in squares. Now the only exception to that is the, to be honest, the Taito 3. I'm using 4 by 4, which I'm kind of using smaller tiles, but as I say, the concept still stands, and I've just quadrupled the size of the screen because of the 4 by 4 tiles. So that's the only exception. Now this small screen option is just another slight tweak to the code. If you think of the evader going across the screen and dropping blobs, because the screen's half the size, to make sure it drops one blob approximately, you have to double the random probability. So the small screen option just changes some of the rules a little bit to make the game work better on a small screen. It doesn't really do very much. So that's all it is. This V9K option is new. This turns on the V9K functionality. If you build this on an Amstrad CPC, then it treats the CPC as a console, because as I've said, V9K is a dedicated video accelerator, can't be treated as a bitmap efficiently. So we are using the console code. So this is new, and as I say, I can't test it. I've got no hardware to test it, and there's no emulator that it works on. So maybe it works, maybe it doesn't. All I can tell you is as soon as I get the hardware, I will do everything I can to make it work. So maybe download the latest version, who knows. So if we've not defined a 4-color palette and we've not defined a Game Boy palette, then by definition we're using a 16-color palette. The palette definition code I'm using is common to all systems, and if you try and run it on a system that can't take a palette like the MSX, it just ignores you. So that's why there's no 2-color palette option there, because there's no need for one. So this is a bridge to allow this code to compile on WinApe or Vasm. I've been using Notepad++ for almost all of this coding, and I've been using Vasm for the compile for almost all of the coding, so I haven't really used WinApe at all, but it should still compile fine on WinApe. Now going on from that, we've got some reads in. We're just reading our generic header, which is the tutorial header, which is just the definitions for the start of a cartridge or whatever device the system's using, just loading in the absolute critical things like a few system functions, but no, there's nothing massive in there. Now, if we're using a console system, we load in this VDP memory function. This is a function that handles the hardware-specific requirements of the system, like selecting a tile, sending data to whatever the hardware is. It's very, very hardware-specific. As I've said before, this will be covered in a later tutorial. The bitmap memory header is similar, but this is for the bitmap-based screens where you can select a line and a byte and then push data straight to that byte. So this has already been covered in the tutorials. Now, it should be said that some of the systems, like now the MSX2 and the MSX1, can work in either mode, but the bitmap memory mode is very slow, whereas the VDP mode, because it's it talks more directly to the hardware's way of working, is much faster. So really, I've left the support for the MSX1 without VDP in. Here it is. You could run these out or run these out if you want to build the MSX2 version or the MSX1 version without the VDP support, but it's slow and there's no benefit to it, so I wouldn't suggest it. So then we've got, we need, on all of these systems, because most of these are running from ROM, things like the Game Boy, it's ROM I'm running from, so self-modifying code is now out the window, so there is no self-modifying code in the common code. Obviously some of the functional code might have it, but the common code has no ROM function, has no self-modifying functions, so we've declared a pool of memory that we're using for all of our variables and functionality. The memory location varies just depending on the system, on what memory location is free, so that's all I've defined there. And then all of my definitions that the game uses are defined as an offset from that starting position so that it's easily moved around. So these monitor functions, these are temporary variables for a special version of my debugging monitor which shows registered states and things. Now it used to use self-modifying code, but I'm using a special converted version that does not, and so it just needs some temporary variables here to do that. Now beyond that we have a keyboard scanner. This is used by the non-console systems, so to read in the lines of the keyboard. Most systems use 8 to 10 lines, but this definition is for 16. So this does need to be byte aligned, by the way, just for the key press function, but as long as it starts from 0, 0, you know it's going to be. So that's why there's no kind of align function here. So player position, these two. Random seed, I've got a random number generator. Fast growth accelerates the growth of the mold at the start of the game, so the player can't immediately kill it. Player direction, which direction the player's facing. Bullet X and bullet Y, the position of the bullet. Nothing shot. If the player isn't shooting anything for a while, a counter starts increasing, and if it seems like the player's got nothing to shoot or they aren't trying hard enough, then more invaders will come in and drop more mold to keep the player active. Allowed fast growth, this is... sorry, I explained it wrong before. Fast growth is if the mold is currently growing fast. Allowed fast growth is if the next mold will grow fast. So they're sort of a combo. Basically, fast growth is set to whatever allowed fast growth is, and allowed fast growth will be 0 if the nothing shot is currently low. Bullet direction, this is the movement direction of the bullet, because of course once the bullet is fired, it takes the current direction of the player, but if the player turns, the bullet doesn't suddenly change direction. Playing SFX, the current sound effects being played. I'm using a sound driver that takes a value from 0 to 255, so it's a single byte. Control mode, the game supports 2 control modes: a single fire mode where you hold down fire and press a direction to turn the ship, or a 2-button fire mode where the 2 fire buttons rotate the ship. The player fires all the time. Game tick is just a counter that constantly goes up and allows the game to decide what to do next. Lives, how many lives you've got. Animation frame, this will be either 0 or 16. It's added to the current tile because there's 2 tile maps for the 2 frames of animation of each tile. Score, this is 4 bytes of binary coded decimal, which is the current score. High score, 4 binary coded decimal bytes of the high score. Animation tick, this is a counter. The screen is not updated, the animation of frames aren't updated all at the same time because the screen's quite big and some of the systems are slow. So it tends to update 1/6 of the screen, so this goes from 0 to 5. That's all that's for. Kempson on, this is used by the Spectrum. If the Kempson is red when there's no Kempson port, then it can come up with errors, so by default it's disabled, and this is just a flag to note if it's enabled. Memory wasn't a problem here, so things like the keyboard scanner and Kempson on are defined even on systems that don't need them, because this is only a handful of bytes. Tile map is the screen. There's 2 versions, so each position on the screen is a byte. That byte can be from 0 to 16, which is the tile that's selected. If you look at the sprites in the previous episode, you'll see how they work, but basically 0 is blank, 1 to 4 is the ship, up, right, down, left, and then the bullet is number 5, and then up to 7 is blank, 8 is the green blob, 9 is the blue blob, 10 is the seeker, etc, etc. Now there is a second set, the second frame of animation, but those aren't used in the tile map, those are added programmatically later. Tile map 2 is a copy of the old tile map, and this is used to see what's changed on the screen, so that the refresh only updates what has actually changed, because of the systems, some of the systems being very slow. You don't want to update more of the screen than you need to. The game doesn't use a double buffer, it doesn't need one, because it's essentially it's only updating what's changed, and it's using checkerboard patterns, so it updates in parts so that you don't see nasty wiping effects, so it doesn't really need it, which is handy because it makes my life easier. We're just disabling internal interrupts here because we don't use interrupts. The sound system's too basic and there's no music, so it doesn't need it. Now here we're defining the memory location of where we're going to start writing the sprite data to. This works in very different ways depending on the system. But so in some systems we're defining a memory location, in other systems we're defining a tile number, but either way, however we end up, we use this define tiles function to actually send the data. Now on the MSX1 we do actually have to do some extra work. The MSX1 has palettes that are specific to the tiles. The color information and the bitmap information are separate. Now rather strangely it uses the exact same amount of bit of data for both. So we actually We use the same function, we just do an offset to the palette data location, which is here, and then we just send the data using the same define tiles function. The define tiles function is just using whatever system the hardware requires. In the case of the MSX, it's out commands, and it's just systematically sending BC bytes from HL to whatever the system requires, and it's using the DE, but the way that DE works, it varies wildly just depending on the system. As I said before, we'll cover it in detail later. We wipe the game memory because we don't want any junk in there sending things crazy. We turn the joysticks on all systems except for the Spectrum, and we initialize the keyboard reader if we need to. Now we set the default control. We set the control mode here, the default, depending on the system. On most systems, it's 2 button, but on the Spectrum and the SAM, which tend to only have single buttons, it's 1 button. We then start up our random number generator. The random number generator constantly changes, so we just pull a random number, but we never use it, and that initializes it. We can support the CPC Plus. The only benefit is you get slightly more subtle color palette, but apart from that, it's the same. Now, the ZX Spectrum is using the internal beeper. On the other systems, it's using the AUI sound chip, but the internal beeper is being used on the Spectrum. The internal beeper actually stops all processing power while it's working because it's such a crude system. So, whereas most of the systems use a common sound and will keep playing that sound even while other things are happening, on the Spectrum it won't. So we've got this special function to set the speed for the ZX. Again, I'm going to cover this in a later lesson. Now, we're defining 32 colours on the Game Boy Color, but on all of the systems we're defining 16 colors plus 1 back border color. Again, some of the systems don't need that border color, but they will ignore it if we try to define it. So we just default to 17, point to the palette we're going to use, and then we use this set palette command, which is going to be covered in the tutorials later to set the palettes. So here's our title screen. We've got a bitmap called title pick. We need to slightly relocate ourselves if the screen's too small to show it all. We also need to center it, and then we dump it to the tile map, and then repaint it. We've got a Kempson message saying press J for joystick or K for Kempson, I can't remember which it is, but that only shows on the Spectrum here, and only if you've not already pressed it. There's no way to turn it off, but if you've turned it on and you've not got one, your system's probably now unusable in my experience. But anyway, so then we show the high score message. And then we've got a piece of code here, and what it does is this is showing a scrolling message. I don't know if you saw earlier, but there's a message that scrolls. The way it works, it starts from text position 0. If it's not showing 32 characters or the width of the screen characters, then it will move across to the right and to the correct position. If it's showing all of them, then it starts at the far left and prints 32 characters worth. If it goes past the end of the string's marked by a 255, then it will pad it with space characters. So that's just a scrolling message. It will loop indefinitely. You can see it at the bottom of the screen. And then we're just doing some animation to make the tiles of the front screen animate. We're waiting for a fire button. If the fire button's pressed, we start the game. However, if the K key or the J key, I can't remember which, is pressed, and this is hardware specific. This is dependent on the exact position and bit of the K key on the Spectrum in the key map. Now we could have used our convert key press to letter key function, but because we're doing this just for the Spectrum, it seemed more sensible to ignore that advanced functionality and just read that one K key in on that one system directly like this. So that's what we've done. And we just loop if they've not pressed the fire button. So we're starting the game, set the lives, reset the score, clear the screen, redraw it, position the player in the center of the screen, start the player firing, because the player fires all the time. There's no bullets, there's no count on bullets, and there's no penalty for shooting. So rather than having to fire them, which you would just be usually wanting to hold down all the time, I decided to make the game constantly fire. I don't think there's any real disadvantage to it, so there we go. So we start off with 2 ticks of fast growth, and we create 2 invaders so that some grime is likely to start with the game. And then we reset game ticks to 0. So the game loop, we pick a random number out, always updating the random number, and depending on that value we might create an invader that comes across the screen or a descender which drops from the top. We see if there's any fast growth. If there isn't, then we don't do anything. If there is, then we force an evolution tick, which is where the grime gets bigger. Now depending on the game tick, we will either do an evolve tick anyway, or we will do a move tick. Now a move tick is where the seekers get closer to the player. An evolve tick is where the mod gets bigger. Now, depending on the current tick, we may not actually want to move the seekers, because if they move too fast, the game will be unplayable. So every other tick, we actually don't move anything. We just do a pause. Now, the pause, all we do is we do an animate, except for on the MSX2 if we're not using the VDP. So this function actually never runs anymore. This function actually always runs now, but before on the MSX2 without the VDP, the system was too slow, so it wasn't appropriate to animate. But the animate function here will update 1/6 of the frames, just to make everything animate and look nice. So the Game Boy and the Sega Game Gear, because the screen's very small and the GPUs are very fast, we need to slow things down a little bit. So we've got a little pause command here, and then we repaint the screen. On the TI 83 we can't show the score, there's no screen, and we can't show the lives because the screen's too small. So, but all in all of the systems we show those at the top. Then we check if anything's been shot. If nothing's been shot for a long time, then we launch 2 invaders and a descender just to give the player some hassle and punish them. And we set the fast growth to 2 so that next time some mold is dropped, it will grow fast for 2 ticks to make the player busy again. So if the player is active, then we reset, nothing shot. So then we read in the player position. We check if the player is still alive, which means checking if they're against the edge of the screen, and if they're not, reading the top, bottom, left and right tiles around the player and seeing if they're all full. If they are all full, then the player's dead. If any of them are empty, the player is still alive. We read in the controls and we start processing the controls. So we wipe the previous playing sound with a 0, because 0 will stop the sound. We check the control mode. If the control mode is to 2-fire mode, we jump down to that. Otherwise, we use the single mode. The way the single mode works is it checks the direction buttons, and then it checks the fire buttons. If the fire button is not down but the direction button is, then it sees if the player can be moved and tries to move the player. Now, at this point, we've done all the movements, and so we merge in with the 2-fire button mode code to run the common control mode. So here's the 2-fire button version. So we've got the up, down, left, right controls here, and we're just checking the screen positions to make sure they can fire. And then we've got 2 rotation buttons here. So all we do is we load in the direction and decrease and increase it and check if we've gone over the limits and rotate it around to the other side. Very simple. So when we get here, we check fire button 3, which is usually, I think that's space or enter or something on the non-3 fire button modes systems. But if you press it, you will toggle between the 2 options. Just in case you do have, if you don't have a 2 fire button joystick on an Amstrad, you will want 1 fire mode. But if you do have one, you want 2 fire modes. So just a simple way of toggling there. Now here's our pause function, because we have a pause button as well. We just show pause on the screen and then wait for a key. The debounce function will just wait for the fire button to be released so that we don't immediately carry on the game or something. Then this is the function that handles if the player has actually been moved. So we save the new location. We first we check if the player can move. If there's a tile in the place the player wanted to move, they can't move. If they can move, we update the player's location in the memory bank here. We then wipe the tile the player was, and then we start doing more checks. So here's the code that handles the bullet. We read in the bullet's position. We check if we delete the old position. We check the direction the bullet's going. We move the bullet. Check if the bullet's gone off screen. If it hasn't, we read in what is under the bullet. And if the bullet has hit something, we go to the bullet strike code, which will handle the bullets hitting something. Now we do multiple. The bullets move basically 4 tiles per frame of the screen animation. So we run this procedure multiple times. Now if you wanted it to move 8 frames, you could just change this to 8. Now you might see from time to time these weird commands here. Well, what are they? Well, the GB Z80, the Game Boy's processor, isn't a true Z80 and it's missing a lot of commands. And one of the commands it's missing is it's missing the IXL register and the IX and IY registers. So I've created macros that emulate those commands. So when you see a command like this, what this means is Z80 load IXL, A. Now if you are running on a Z80, this will run with the real command, but if you're running on the GB-Z80, it will run an equivalent emulated command, and if necessary in this case, the register will actually be a memory mapped variable. So This allows me to have the speed and flexibility of the Z80 processor, but allows me compatibility with the GB Z80 that doesn't support those commands. So when we get down to here, we repeat until all of the bullet recalculations are done, then we draw the bullet here. Now a bullet restart means the bullet's gone off screen or hit something. We need to set it back to the player's location and set its direction back to the player's. And then we find the tile we want to draw. At this point we save the current location of the bullet, we set the current tile to number 5, which is the bullet, and then we draw it. And then we load the player's definitions back in and we redraw the player. Finally, we take in the sound we want to play and we run this sound module here, which is Chibi Sound, which is my sound driver. Very simple, can only play one sound at a time. It's a beep from low to high, it might be noisy. We're going to cover that in the tutorials later. The descender is the object that drops from the top of the screen. We just load in a random top line and set the tile to 12, which is the descender sprite. The invader comes from the right hand side of the screen. We select a value from 0 to 31, and then we multiply it by 32 to get the tile position of one of the far right tiles, and then we set it to 11, which is the invader tile. Don't know why there's 2 of those, they don't need to be, but never mind. These XORs here before the return are because it's going to drop straight back into a compare command and to compare the tile that it's currently looking at. So it's basically causing the end of that comparison. So the player's been killed once, so we load in BC with 1000 here. Now this is the sound effect and also the loop counter here. So we push it here just because we need to back it up. We find a random column, see where the grime is currently descending down the screen at that position. Once we've found it, we update. If we've got to the end of the screen before we found one, then we just ignore it. And then we keep repeating. We tweak the value down of BC down to a value from 0 to 63, which is what Chibi Sound wants for its sound effect. We want a noisy sound effect, so we set the top bit to 1. We set the 6th bit to 0 because we want a quiet sound effect. 1 would make it louder and it would be too loud. So it's just a very simple sound driver here. And then every so often we will update the screen. We don't update the sound or the screen too often because it would slow things down. Now we keep repeating. Once we've finished that 1000 loop, we turn off the sound because we don't want a noise. We then fill the entire map with 13, which is the descending mode, because we might not have actually randomly filled it all, so that's just a sort of fill in there. We do a quick pause, and then we decrease the lives. If the player's got lives left, then we carry on with the game. If they've not got player lives left, we put the game over message on screen. We then use the binary coded decimal compare to check if they've got a new high score. If they have, we update the high score and tell them they have. If they haven't, we just wait for the fire button. Now on the tie, the high score there was no room on the title screen to show the high score, so we only show it on the game over screen. Here's the messages for the game over. Very, very rude there. But, I like a bit of rudeness. The bullet strike code here. We need a score. The binary code, the definitions of the scores have to match the size of the thing you're adding it to for my binary coded decimal code. So we've got some definitions at the bottom here for 1, 3, 5 and 20, and depending on what you've hit, it varies the score. So we're loading in the score, we're loading in the sound effect, and then we're comparing to see what score we're actually going to apply. When we get here, we load in that sound we're going to play from A and store it in that temporary variable here. Then we load in our score and we use the add function. These were in the tutorials advanced lesson 2, I think it was. So this binary coded decimal functions are already in my tutorials. And we remove the tile that was shot here. We clear the nothing shot variable because the player is being busy, and also we stop the fast growth from happening again because the player is busy. And we get another random number because the player hitting stuff is likely to be random. It's a good way of keeping the random seed going. How do we get that random seed? Well, here it is. Well, we get the R register. Now on the on most of the systems, the R register is a real thing. On the Game Boy Z80, there is no R register, so we're simulating. The way I'm doing it is I'm XORing pretty much all of the registers together just to get something vaguely random. It's not made. Random numbers weren't really a priority in this, and we shift the current random seed 1 to the left just to keep everything sort of ticking strangely. And we XOR in that R register or whatever we loaded, pretending it was the R register. Pause just waits for the value of BC, just a simple thing. Read controls uses the joystick reading code, which I'm currently covering in the tutorials. There's two joysticks defined. One is actually the keyboard and the other is the joystick, and they're ANDed together, so that if either one is pressed, it has the same effect on both, because we only have one player, so why not? Debounce is just a simple thing. It reads all the controls in and makes sure nothing is pressed. This is for pause and things, and when you need to make sure that the player fires to continue, you want to make sure the player hasn't got fire held down before you continue. So that's all that's for. And wait for fire is here. We debounce first when we read the controls. We are in the any fire, which will set the non-fire buttons to 1. If the resulting value is 255, then we're not done. If the resulting value is not 255, then one of the fire buttons must be down, so we can actually return. Clearing the screen just sets the entire tile map to 0. Force animate, this is a little bit tricky, but it's not too bad, for the count of 1/6 of the screen, and we move in 6s. The reason we do this is because it gives a kind of random looking pattern, but it's not random. So it's fast to do, but it doesn't make the screen update in weird patches. All we do is we load in the animation frame, and we toggle it with number 16 once we're done, and that will show the second frame. But then when we're going through the tile map, what we do is we check if a tile is 0, because if a tile is 0 we don't want to update it, because that will slow things down, because tile 0 is black, so there's no second frame of animation. If it's not black, then we set it to 255. There is no 255. We're setting the old tile map so that the system thinks the tiles have changed and forces them to refresh. Force repaint is also working on the old tile map 2, and it sets all the values to 255. Now this is used for the start of the game and when the pause button's pressed, times that you can afford a full screen refresh. As I say, it's quite slow. Updating 1/6 of the screen is very fast. Updating the full screen is very slow. So we don't want to be making things slower than we need to. So forcing everything to update, whether it's changed or not, doesn't make sense. Now here's the main repaint function, and you'll see it does this do fill command 4 times, and this is the checkerboard function that I described. So basically it's moving in across the screen in 2s and down the screen in 2s, and then it does, if you think of the top 4 squares as being the top 2x2 squares as being 4, the top left corner would fill first, then the top right, then the bottom left, then the bottom right. It gives it this kind of interlaced checkerboard effect fill, and this means that you don't see a visible wipe. It just updates the screen much more naturally looking and much faster. So that's why we're doing this. And you can see here this do fill command is doing ink B and ink C twice, and that's because it's moving in pairs. Now the render tile function is what's actually doing all the work. There is a slight difference between the functionality on the most of the systems and the TIE 8. The TIE 83, the reason the TIE 83 is different is because its tiles are 4x4 squares, but its data is 8 bytes wide. So there are actually 2 tiles in a single byte, and that means we have to render the tiles in pairs. And so because of this, we skip every other tile because we already rendered it in the last pass. But this function isn't just drawing things, it's actually already also updating tilemap 2. Tilemap 2 is 768 bytes after tilemap 1, so we're getting its position with this add command here, and then we're updating tilemap 2 to be the same as tilemap 1. This saves an LDIR doing the same job later, and we're already scanning over the tilemap here. So here's the evolve routine. This is where the mold gets bigger. So we load in tilemap 2 here, and we are using tilemap 1 is 768 bytes before tilemap 2, so we can get to tilemap 1 just with this subtract here. So we're reading in tilemap 2, which is the one that knows what's currently on the screen, and then we're updating tilemap 1 here with what's going to be on the screen next. This is why we need the 2 tilemaps, because otherwise when we updated the new one, if we were reading the new one as well, we'd end up reading our own data and end up in an infinite loop. So green mold is one kind, blue mold, descenders drop from the top, invaders come from the side, and seekers seek. And we'll have a look at what they do later. So we just repeat over the entire map here. Mold move, this is a simpler version where we only do descenders, invaders and seekers, basically things that move every frame. So here's the descender code. What does it do? Well, it reads in the current location, adds 32, which effectively moves it down a line because the lines are 32 bytes wide. And then it updates the position. It checks if we've hit the player and kills the player if we have. The descenders also affect the mold. The blue mold turns green, and and the seekers turn blue. So it has a kind of morphing effect on the mold that it passes over. Now it's also reading in the tile below it and replacing it with the tile it just passed over, and this is because it doesn't have a buffer to know what really was under it, so it's actually shifting things as well, but it's just a crude effect. It does work well enough. Invaders are kind of similar. They move from the right hand side to the left, so again we're checking if the player's dead. Now we can just get that effect of moving to the left just by decreasing HL here, but they do have another effect. They drop new pieces of the grime mold. The frequency varies depending on the screen size, because as I said before, the small screen size needs to increase the frequency because of the screen so much smaller, and we want the same number of molds to drop with each flying pass. If we got non-zero, then we're not going to drop a spore, but if we got a 0 from this calculation, we are going to, and all we need to do is set A to 8, which is the green mold spores. Now if we're going to do fast growth, now's the time to apply it, so we do. And then we load the new value, which is either the old position or the new grime. Now if we've gone over a player bullet, we want to remove that, so we set the old position. If we've gone over the player bullet, we need to set that to a 0, because we're swapping positions. We don't want to make a mess, and it was cloning bullets, so that's what that's for there. Now the seekers will read in the player's position, work out the relative position of the seeker to the player, and will attempt to move towards the player here. If the seeker is able to move to the player, then the new position is updated here. Now the green and the blue mold have a special evolve routine here, and what each one of them does is they both follow the same rules. A green blob will be replaced with a blue blob, and the 4 surrounding up, down, left and right blobs will turn green. The blue blobs are very similar. The blue blob will turn to a seeker, and the up, down, left and right will turn blue. So they both share the same evolve function, and we use IXH and IXL to define the two kinds of mold that will grow. Now again, we're using these macros because the Game Boy doesn't have those registers, so we're faking them. So here's the evolve routine. So we're setting HL here to the new mold, and then we're moving up. We're moving right, left, down and up here, assuming we're not already at the end of the screen, and we're setting the mold accordingly. And then we just move back to the main loop, which is evolving that mold here. Find tile, we can get a memory position of the tile based on a BCXY coordinate. Now the tile map moves across first and then down. Each line of the tile map is 32 bytes wide, so basically we multiply y by 32 and then add x, and then add that to the start location of the tile map in memory, and that's how the memory position of the tile. Pretty simple. Render tile does the actual drawing work. Now on the tie, it does have to read in 2 bytes, and that's why it's got these IXH and IXL. Notice I'm not using the macros here. The reason for that is because this never runs on anything except the TI-83, which is a true Z80, and not the Game Boy, which is a fake Z80. So that's why I'm not using the macros here. But here is the regular version. We just load in a single byte from HL into A, and that's the tile. But we also need to load in the animation frame, because if we're showing the second animation frame, we OR it in here. So we load in there, store it in B, OR it in, and that will add 32 if we're showing the alternate frame. These are for the SAM Coupe, which need the bottom memory bank switching, so we can draw to the screen, and then we run our show tile routine, which is in the simple tile function we're going to have a look at in a moment. Here's the palette definitions. Now these are in a common format, which is based on the Amstrad CPC one. I've written emulator code that uses these common definitions on all of the systems, so you can see whether it's the Amstrad CPC, the SAM Coupe, the ZX Spectrum. ZX Spectrum doesn't have palettes, what am I talking about? The MSX, the Game Boy Color, the Game Gear and the Master System, which are virtually the same system, but ironically have different palette definitions. So I'm using this common palette definition for all of the systems, which is why I've only got a 16 color palette, a 4 color palette, a Game Boy palette, and an MSX palette further down, which works differently because that's applied to the tile map. But it's allowing me to have a common palette for all of the systems that need that number of colors. So, and that's been a big saving in this program. And it was also why Chibi Ackerman's for the Enterprise was finished in 2 weeks and not 2 months. So we've got our simple tile function here. There's the main one for all of the systems and the Chibi version for the TI-83. Here's our font. We're actually using the 96 tile font for about all of our systems because we don't have any memory problems. Here's the bitmaps. Now the bitmaps vary depending on the system. The 4-color systems use the CPC ones. The 2-color system uses the ZX Spectrum ones. The tie uses the miniature one for the tie. Here, the Game Boy Color one uses the special Game Boy one. Game Gear Sega Master System uses the Sega Master System one. The MSX one, because it's 2-color, uses the ZX Spectrum ones. The MSX2 uses the MSX2 one, which is in the same format as the Sam Coupe. Now, some of the 16-color systems, like the Sega Master System, because these need to match the data format of the actual screen hardware, they are different. Now, why are there 2 for each? Well, this is the first set of frames, so there's 16 sprites in there, and this is the second. To be honest, I could have merged them into the same file, but I added the animation later, and it didn't really feel worth the effort. So the systems that are palletized, here's the Spectrum palettes. This is for animation frame 1. This is for animation frame 2. They're the same, of course, but just why not? Here's the definitions for the MSX palette. Now you'll notice there's 1, 2, 3, 4, 5, 6, 7, 8 per tile, and that's because each line has 1 byte for the bitmap data, which is black and white, and 1 byte for the color information. 1 nibble is foreground and 1 nibble is background, and there's 16 colors for each. Much nicer color palette than the Spectrum, but that's by the by. The Game Boy Color has palettes. Each palette is 4 colors, and so this is the palette that tile is going to use. Now the Game Boy ignores those, so we don't need to worry about any Game Boy palettes. The Game Boy palette is defined as just black to white, white being the highest color. Here's the default key maps for each system. In all the cases, the first definition is the keyboard, WSAD, B, N, M, B, N, and M, and P for the fire buttons and pause. And then the other controls are the joystick, space, and enter, and pause. Here's the binary coded decimal definitions for 1, 3, 5, and 20 in the format that my code needs them. This is the definition of the title screen. It actually uses the tile map, so these are the tiles that make up the Grime Z80 logo. Here's the press K for Kempson message. Here's the scrolling message. Here's the patron backers who were kind enough to back me, but unfortunately they did not appear in the scrolling message because of the 255 character limit. So unfortunately only my higher backers were able to fit in. Sorry about that. High score message, smaller on the tie because the tie screen is so small. Pause message. Debugger here, special version that doesn't use self-modifying code. Show hex also used for that. Binary coded decimal function. Chibi sound function, we'll be covering that in a later tutorial. VDP memory, be covering that in a later tutorial. Hardware tile array, be covering that in a later tutorial. Bitmap fonts, I think we've already covered that. Bitmap memory, we've definitely covered that. Read joystick, I think we're covering that this week. And so, as I say, all of this is generic tutorial code which you can download now, and there are tutorials covering it. If there aren't yet, there will be very soon, so please watch this space. Don't forget to subscribe to my channel, thank you. So let's start off with the Chibi simple tile because it's quite short and it's much simpler. So we've got this is not true, it's not the tile number in A, it's in IXH and IXL, but BC is the XY position of the tile we want to show. Because we're working in byte pairs, we have to shift X along 1, and because each tile is 4 lines tall, we have to multiply this by 4. So we're doing this with bit shift here. We then get the hardware screen position of the byte. We read in the first tile, which is the left-hand side tile. We do some shifting to move through the sprite definitions to get the correct tile we're going to show. We then add that to the start position of the bitmap memory. We then back this up. We do the same for the right-hand tile map, and then we pop off the alternate tile map in IX. So we've got one tile bitmap in IX and 1 tile bitmap in DE. We're going to have to show 4 lines, of course, so we want both at the same time. So what we do is we load in the left tile, the 4 bytes of the left tile, and store that in B. We load the 4 bytes of the right tile. We need to shift those to the right, so we do these RCAs here. And then we OR in the left tile. We now have the entire tile line, so we set it to the screen and repeat. And we just do that 4 times until we're done. 4 set. Now this is a little bit more complex because this does much of the work for the tile map on all the systems, and our systems are very varied. So the first question is, well, how many bytes wide are the tiles? Well, on 4-color systems they're 2 bytes, on 16-color systems they're 4 bytes. And on 2-color systems they're 1 byte. Now, VDP systems, we don't need to know that because they work in tiles, not in bitmaps. So if we were working on a Sega system, get the memory position of the tile we want to change. We have the tile number we want to show in A. Now the sprites start at tile 128, so we add 128. We write it to the memory position that they selected. The tile definitions are 2 bytes, so we add 0 to the second byte. Now on the Game Boy systems it's kind of similar. On the color systems we have palette work we want to do as well. So first we get the palette definitions, we add the current tile to that palette definition location, and we store the location that we're going to do. Now we need to get the memory position of the tile we're going to change as before, and we do that here. And then once we've done all that, we then just add 128 again, because that's where our sprite definitions start in the tile map. The first 96 are, of course, the characters A to Z, etc. And there's some space between, but I wasn't going to end up using many tiles, so it just started at 128 for cleanness. Now this is the command that actually sets the tile, because this command has selected the memory location, because it's a memory map memory location, so we just set this to 128 plus the tile we want to show. If we're on the Game Boy Color, now is the time we're going to use this. So we stored D here, and we stored it on the Game Boy Black and White as well, but it doesn't make any difference. It's this. We can't run this on the Game Boy Black and White. What this does, this is a memory map register which turns on the Game Boy Color memory, and then we write the palette information to the Game Boy Color memory. So if we actually ran this on the Game Boy Black and White, I think what would probably end up happening is it would corrupt the tile, because this wouldn't have any function, and then it would overwrite this memory, which is the tile's selection memory. So as I say, that's why this bit is color only. This bit, it's a bit of a waste of processing power, but we had processing power to waste, so what. Now here's the main code, which is running on most of the bitmap systems. So we need to convert X depending on how many bits are on this each tile takes up. We convert Y because we need to multiply it by 8, because we've got 8 lines per tile. We then load in the tile number. We shift it to the left so that we've got the tile number times the number of bytes per tile. We then load in the bitmaps, add in that number, and that's pointing us now to the correct tile that we want to show the bitmap data of the tile. We then get the screen position, which is using our BC. Now we're going to draw 8 lines. Again, we need to loop depending on how many bytes we're showing. If you wanted to speed this up, this is where you could really optimize things. Take these loops out and hard code it for all of the screen definitions. Obviously, there's a lot of things I could have done to improve this, but the speed was good enough, and I was under a very short time limit. So this is reading in the byte data, sending it to the screen, increasing, getting the next line once you've done a line, and then doing all the lines, and then we're done. Now on the spectrum, we also need to set the palette definition, so we use get call mempos. We read in the data from the palette according to the sprite here, and then then put it to the screen memory. On the MSX, it's pretty similar, but we have to do it 8 times, and because we're doing it 8 times, we have to do some bit shifts to move along to the appropriate palette definition for the current tile. Now that's not really going to be used very often, because we've now got these hardware tile definitions. That would be used only for the bitmap version, which we're not really using anymore because it's too slow. So this is the better version, and it's much more similar to what you've already seen for the Game Boy Gear. We get the memory position of the XY coordinate. We add 128 because the sprite tile starts at 128, and then we send the data to the VDP, and that will do it. Now, if we're running this, when I say MSX1, that means the MSX1. When I say MSX, I mean MSX2. I tend to think of the MSX2 as being the main system because it's so much superior to the MSX1. I mean, you could argue that this definition is wrong, but by the time I got to this stage, it was kind of too late. As I said before, I was under some quite considerable time constraints of only having 7 days to write this. So again, what are we doing? Well, now we load the destination location into D and E. We load H with 0, L with the tile we want to show. Remember adding 128, and we'll call this copy tile to screen. Now on the MSX2, I should point out, it's not actually a hardware tile map screen. It's a bitmap screen, but it is good at copying chunks. So what I've done is I've written an emulator that works the same as the other systems, and it uses a piece of off-screen memory, and it creates and copies that in 8x8 chunks. So this is using a hardware copying command, and that's why the definition is very slightly here with regards to using DE as the destination locations and HL as basically the source tile number. So as I say, not quite the same, but it works almost the same for our functions. And this is the V9K version for the Amstrad CPC, which is identical to this. Now, in case you're wondering where the V9K version of this is, there is no version. The reason for that is the driver, if you will, the code that I've written to support the V9K and the MSX2 hardware is identical. It takes the same parameters. The way it talks to the hardware is slightly different, but it takes the same parameters, and that's why Chibi Akuma's works so easily on MSX2 and MSX with the 9990. And so again, hopefully I can support the Amstrad CPC here with no extra coding at all, just by turning on some of the MSX modules for the Amstrad CPC with that V9K. Well, I apologise, it's been quite a fast run through here, but you know, I didn't want to spend the rest of my life on this project, so I have been going through it quite quickly. If you've got any questions, you know, just put them in the comments, and if I can, I'll answer them. All of this has been gone through in more detail in the previous episodes of Grime Z80, and the code that I've not covered today, the joystick code, the display code, that's all either in the tutorials or it will be in the tutorials very soon. So please, you know, stick around for that too. I hope you've enjoyed Grime Z80. I hope you've enjoyed this series. I think it's been very productive. I was sort of confident I could create it, but I really didn't think that what I've achieved, I think, was the absolute ideal that I could possibly hope for within 7 days. It's really gone as well as it possibly could have, and it's given me a lot of confidence that I've succeeded at such an ambitious project, to try other projects in the future in this way, multi-platform, even more so now, maybe with the CPC V9K and things. So I'm planning to do more of these in the future, but I actually had to take time off work to do this one, so it's not going to be for quite a while. You know, maybe I could manage one at Christmas or next year, but it's not something I can do every week or anything. But anyway, please follow my channel, please follow my tutorials if you enjoy this kind of content. Thanks for watching. Take care now. Goodbye.